Welcome viewers to the fourth lecture for the online series of lectures for the course of Algebraic Topology 1. In the previous lecture, we have been introduced to the notion of covering map and local homeomorphism. We got to know some results concerning these two notions. In the process, we saw that the restriction of a covering map is not necessarily a covering map. We have seen a counterexample demonstrating this fact. In the process, we also got introduced to this very important example of the covering map from the set of real numbers to the unit circle. In this lecture, we will first have the definition of something called lifting of a continuous map. Let me give you the definition first. So let P from E to B be just a map if F is a continuous map of some topological space X to this topological space B, then a lifting of this map F is a map F bar from X to E such that P composed with F bar is equal to F. In other words, the following diagram commutes. From E to B is the map P, and then we have another topological space X from which we have a map F onto B, and then the lift of F is a map from X to E denoted by F bar such that this diagram commutes. Okay, in other words, this equality holds. In this lecture, we'll be concerned with liftings when E is a covering map. That is, this map denoted by P should be a covering map. Okay. All right. So let me have a motivating example. So for the results to follow. This example is related to the familiar covering map denoted by P from the set of real numbers to the unit circle. Given by P of X is equal to cosine 2 pi X sine 2 pi X. So we'll consider three different paths on this unit circle, okay, and compute the relevant liftings. All right. So first of all, we consider a path F, which is of course a map from 0 to 1 to S1. So this is a path in the unit circle. Okay, and this is given by the following formula. F of s is equal to cosine pi s sine pi s. Okay, all right. So we need to construct the lift of this path on the unit circle. Okay, let me give you a second example here on the right side, which is given by, so it is another path on the unit circle. So let me denote it by G instead of F. Okay, and this is given by the following formula. G of S is equal to cosine pi s and minus sine pi s. Okay, so let me draw a diagram denoting the situation, describing the situation. So this is the real line, 0 is the origin, this is 1, this is say 2, this is negative 1, this is negative 2, and then I have 1/2 here, negative 1/2 here, and so on. Okay, so now let me draw the path on the circle. So let me draw a circle here. This is the center. This point lies on the x-axis. Here is the y-axis. This is the origin of the coordinate system. This is x-axis. This is y-axis. Okay, and this point is 1, 0. Okay, and this point is negative 1, 0. Okay, right, and this point is 0, 1. Okay, so pictorially I am concerned with this path on the circle, on the unit circle. Okay, oriented counterclockwise. Okay, and this is a path starting at 1, 0 and ending at minus 1, 0, and this path is of course a map from 0 to 1 to the unit circle, right? This map is F. Okay, and this is a covering map from the real line to the unit circle, and I want to know what this F bar is. Okay, this is going to be the lift from the this is the lift of the map F on the real line R, which is of course a path on the real line. That is a map from 0, 1 to R. Okay, so in this case I have this covering map, which is the real line, and this is the circle. Okay, this is the covering map V, this covering map, and I have this path F from 0, 1 to S1, and I'm looking for this lift F bar that will make this diagram commute. All right, good. So from the lifting property, we want P composed with F bar to be equal to F, right? Because I want this diagram to commute. So this evaluated at S should be equal to f of s, and f of s is given by cosine pi s sine pi s, right? And well, decomposed with f bar of s is nothing but p of f bar of s, right? And which is p of f bar of s. So you have this general expression of the covering map. So you just replace x with f bar of s to have cosine 2 pi times f bar of s, comma sine 2 pi times f bar of s, and that is going to be equal to cosine pi s, comma sine pi s. Okay, so the only way this is going to be satisfied is to choose f bar of s to be equal to just s over 2. Okay, so which means that f bar is a map from 0, 1 to the set of real numbers beginning at 0, right? Since f bar of 0 is equal to 0, and it ends at 1/2, since f bar of 1 is equal to 1/2. So this is the path, 0 to 1/2, beginning at 0 and ending at 1/2. Okay, this is our f bar. Okay, now what's the story of the map of the path G? Okay, well, so something important here is to note that when you choose s to be 1/2, so we say we choose 3 points on this intervals to know what the path actually looks like. So f of 0 is 1, 0, and f of 1 is minus 1, 0. If you plug in 1 here, then you have cosine pi, sine pi, and cosine pi, sine pi is minus 1, 0, this point. Okay, and take an intermediate point, say s equal to 1/2. Then you have cosine pi over 2, sine pi over 2. Cosine pi over 2 is 0, sine pi over 2 is 1. So this gives you this point 0, 1. Okay, so this is the loop that we are looking at. Okay, so now how does this one look like? So we have this real line R. In the middle I have the origin, and then I have 1 here, I have 2 here, I have -1 here, then I have -2 here, and so on and so forth. Okay, so this is plus 1/2, and this is minus 1/2. Okay, good. Okay, so now this is the interval from 0 to 1. Okay, and then I have this circle, right? Here is the x-axis, and here is the y-axis. This is the origin, 0, 0, the origin of the coordinate system, and this is the formula. So I take 3 values. So when s is 0, I again have 1, 0, this point, and when s is 1, the other end point of the loop being minus 1, 0. So if I plug in minus 1 here, I get minus 1, 0. So this guy is minus 1, 0. And when I plug in 1/2 here, then I get cosine pi by 2 is 0 and sine pi over 2 is 1. So I get 0 comma minus 1. 0 comma minus 1. So this is the loop that we are looking, this is the path that we are looking at. Okay, this is not a loop, this is a path. Starting at 1 comma 0 and ending at minus 1 comma 0, directed clockwise. Okay, good. Now let us find the lift. So similar to what we did before, we consider P composed with G bar evaluated at S is equal to G of S, and G of S is cosine pi S comma minus sine pi S, right? And P composed with G bar of S is nothing but P of G bar of S, right? So this is going to be equal to cosine 2 pi G bar of S and sine 2 pi G bar of S from this expression. And we want it to be equal to cosine pi S minus sine pi S. So we want cosine 2 pi G bar S is equal to cosine pi S, and at the same time I want sine 2 pi times G bar of S to be equal to minus sine pi S. And we know that, this guy is cosine of minus pi S, right? By the by the well-known properties of trigonometric functions. And minus sine pi S is going to be equal to sine minus pi S. Okay, so equating these two, so separately, we consider, by considering these two equations separately, we see that G bar of S is going to be equal to minus S over 2. Okay, so it means that the lift G bar is a map from 0 comma 1 to the real line, which begins at 0, because G bar of 0 is 0 and G bar of 1 is negative 1/2 here. So this is the path. This is the path in the real line we are looking at. Okay. Directed opposite to what we had earlier here. Good. So this is the second path. Now we are going to consider another path. Let me erase everything for the same example, meaning for the covering map, which is a map from the set of real numbers to the unit circle. Okay, so now we consider this path H of S given by cosine 4 pi S comma sine 4 pi S. Okay, all right, let me draw the real line. In the middle is the origin, then 1, then 2. On the left I have negative 1, negative 2, so forth. This is 1/2, this is negative 1/2. Okay, so now we have a circle here, then we have a smaller circle starting at the same point, so they are both directed counterclockwise. So the first circle means that it's a loop. This is 1, 0. Okay, so it means that we start it at this point, go counterclockwise, come back to the same point 1, 0, and then we go again in the same direction, counterclockwise, and get back to the same point. All right, 1, 0. So we revolve twice around the circle and get back to the point 1, 0 on the circle. Okay, all right. Now, so this path, the loop, after getting around the circle twice, we end up with a loop that is a path from 0, 1 to this unit circle, right? Given by h. And from this real line, we have the covering map to the circle, to the unit circle. Now I need to know what this h bar, or the lift of h, looks like. Okay, which should be a map from 0, 1 to the set of real numbers. Okay, let's see. From the lifting property, we know that P composed with h bar evaluated at S, which is nothing but P of h bar of S, is equal to simply h of S, which is cosine 4 pi S, sine 4 pi S. Okay, good. And P of h bar of S, according to the definition of covering map, is cosine 2 pi h bar of S, sine pi h bar of S, and we set it to be equal to cosine 4 pi S, sine 4 pi S. Well, so now we set this to be equal to this and this to be equal to this, and the solution is given by h bar of S to be equal to twice S. Okay, which means that h bar is nothing but a path on the real line that starts at the point 0 and ends at the point 2, because h bar of 0 is 0 and h bar of 1 is 2. So this is the path that begins at 0 and ends at 2, something like this. Alright, so when we have this loop that begins at 1, 0 and ends at the same point, and which results in from going around the circle twice counterclockwise, has a lift onto the real line, onto the real line, which is a path from 0 to 2 on the real line. Good. Alright, let us have the first lemma of today's lecture. Let me state it first and then I'll prove it. Lemma 1, which states that let P from E to B be a covering map let P of E0 is equal to B0, any path F which is a map from 0, 1 to this base topological space B, beginning at the point B0, has a unique lifting to a path F bar in this covering space E beginning at E0. Okay, so this is the statement of this first lemma. All right, so okay, let me draw a diagram very quickly. So I have this covering map here from the covering space E to the base topological space B. All right, and I have a path in B, which is of course a map from this interval 0 to 1 to this base space B. Okay, and then I have a lift F bar that is supposed to be unique if corresponding to this point B0 in the base topological space B, there is a point E0 in this covering space E, so that P of E0 is going to be equal to B0. Okay, P of E0 is going to be equal to B0. So the lemma says that if this is the situation, then for this, if this path F begins at the point B0, meaning that if F of 0 is equal to B0, then there is a unique lift of F given by F bar that is going to start at E0. That is, F bar of 0 is going to be equal to E0. Okay, this is what this lemma of 1 states. Okay, so let me go over the proof. Okay, first of all, since P from E to B is a covering map, for every point X in B, we can find an open set in B that is going to be evenly covered by P. Okay, let us denote that open set by U sub X. Okay, so U sub X is a neighborhood of X that is going to be evenly covered by P. Okay, good. Now we can have an open covering of this topological space B, which is this collection, the collection of all such U sub X as X varies in the topological space B. Okay, this is an open cover of B. All right. Now observe that F is a continuous map. F is a path. F is a path in B that starts at the point B0. Okay. Well, that means that F is a continuous map from the topological space 0, 1 to the topological space B. Okay, and since each of these UX's are open, each of these UX's is open in B, the pre-image of U sub X is going to be open here in 0, 1. Okay, which means that the collection of all such open subsets of 0, 1 is going to be an open cover of the interval from 0 to 1. Okay, all right, so we just have seen that this collection, the inverse image of U sub X under F as X varies in the topological space B, is an open cover of this interval from 0 to 1. Okay, and 0 to 1 is a compact metric space. Alright, now I state a very useful lemma called Libec number lemma for our purpose. So let me state this lemma, which is called Libec number lemma, that is going to be used in our proof. Okay, let x comma d be a compact metric space given an open cover u sub alpha, as alpha runs in this index set j of x. There exists a positive number delta called Libec number associated with the open cover such that for a given subset A of x, whenever the diameter of A is less than delta, one must have A contained in U alpha for some alpha in the index set J. Let me explain what it means. So first of all, we are given the metric space, a compact metric space x comma d, okay, and then we have an open cover u sub alpha, as alpha runs in the index set j. This is going to be an open, this collection is going to be an open cover of x. So once we have this open cover, we'll have a corresponding positive number delta, right? So if we can find a subset A of this compact metric space X such that the diameter of A is less than delta, what does it mean by diameter? Diameter means the supremum of the distance between any 2 points of a set. Okay, so if this is a set, then I choose 2 points and choose the distance and find the distance between those 2 points, and the supremum over all such distances is going to be the diameter of the underlying set. So in this case, something like this, the diameter of this set is going to be like this, okay? The biggest distance between any 2 points, the supremum of all the distances. So to be more precise, I should say the supremum of all, the least upper bound of all the such distances between any 2 points of the subset is going to be called the diameter of the given subset. So once we choose the open cover, we'll always have a positive number delta that is going to that will be called the Libec number of the associated with the cover. Whenever we choose any subset of this compact metric space X such that the diameter of that subset is less than the Libec number, we have that subset to be contained in one of the members here in this collection. That's what's written here. Okay, so this is Libec number lemma. So let's see how we are going to use this Libec number lemma in our case. Okay. Alright, so we have seen so far that the pre-image of U sub x, as x varies in the base topological space B, is an open cover of the compact metric space 0, 1. Okay, so we have this open cover. So according to Libec number lemma, I have this positive Libec number, right? Which we denote by delta. Okay, which is the Libec number associated with the open cover we are considering. Okay, so now I'm gonna partition this interval from 0 to 1. The divisions, the subdivisions are going to be as follows. S0 is the first one, then we have S1, then we have S2, goes on all the way up to Sn minus 1, okay? The last one, we call 1 to be Sn and this 0 to be S0, okay? So we have the following subintervals, closed subintervals. S0 to S1, then from S1 to S2, and then from S2 to S3, and finally we have from Sn minus 1 to Sn, okay? Here Sn is 1 and S0 is 0, okay? So these are the subintervals that we get after partitioning 0, 1, okay? So we are going to partition 0, 1 fine enough so that each of these subintervals' length is going to be less than delta. Here, the length of the subintervals, the lengths of the subintervals are precisely the diameters of the corresponding sets. Okay, so diameter of the set of the closed set from Si to Si plus 1, right, is precisely the length of this subinterval, right? Si plus 1 minus Si. And we partition 0, 1 in such a way that that S sub I plus 1 minus Si is less than delta for all I in this finite set, 0, 1, 2, all the way up to n minus 1, okay? So when we have 0, we get this first subinterval, right? S1 minus S0, right? And when I is equal to n minus 1, we have, Sn minus 1, right? This one. And we want all of that to be less than delta, the Libec number associated with this open cover. Okay, so now since this is the case, we according to Libec number lemma, we have this interval to be contained in one of these members of the collection, right? For some x in B, right? For a given I here, right? I here. 0, 1, 2, all the way up to n minus 1. So in other words, what we have found is that the image of this closed interval under F is contained in U sub x for some x in B given for a given I in this closed interval. For I in this finite set. Okay, this is going to be our first equation. Okay. All right. So let me erase this top bar. Good. Now we are going to define this lift F bar from which is a path in the total space E, right? We are supposed to construct this continuous map, which is going to be a path on construct this lift, which is going to be a path from, which is going to be a map from 0, 1 to E. Okay, and we also want this path to start at E0, right? Okay. Well, and since it's a lift, I want it to satisfy P composed with F bar to be equal to F, right? All right. This is what one needs to do, and we are going to do it inductively. So it's going to be an inductive construction. Okay, let's see how we do it. So for inductive construction, we need a base case, and the base case for this inductive definition is the following. F bar of 0 is F bar of the interval starting from S0 to S0 and ending at S0, which is nothing but 0, right? So since S0 is equal to 0, the closed interval from S0 to S0 is 0 itself, right? And this by definition is E0. So this is the base case. Then we assume that F bar on 0 to Si is defined. One has to show that F bar from 0 to Si plus 1 can be defined as well consistently. Okay. Then we are done proving that this F bar can be constructed. Okay, and so we'll be able to prove this only if we can show that F bar on Si to Si plus 1 can be defined, right? Well, since F bar from 0 to Si is defined, if we can define it, if we can define F bar appropriately on Si to Si plus 1, then by pasting lemma it would imply that F bar can be defined from 0 to Si plus 1. Okay, so this is what we need to do. We need to prove that starting from, this is the inductive hypothesis, and we need to prove that F bar can be constructed on this subinterval from Si to Si plus 1. Alright? Okay, let's do it. Let's start from the inductive hypothesis, which says that F bar on this closed interval is defined. In particular, F bar of Si is defined. Okay, which follows from the inductive hypothesis. Now, using the fact that P composed with F bar is equal to F, one immediately sees that P of F bar of Si is equal to F of Si, right? And we remember equation number 1, which says that F of this, the image of this subinterval Si to Si plus 1 under F is contained in U sub x for some x in B, right? Okay, so which means that this guy is contained in that U sub x, right? Okay, and we know that this U sub x is evenly covered by P, so that now using this, so we just have seen that P of F bar of Si is contained in U sub x for some x in the base topological space B. So F bar of Si is contained in the pre-image of U sub x under P, right? That can be written as a disjoint union of open sets V alphas in the topological space E. This is our equation number 2. Now, since this is a disjoint union of V alphas, F bar Si has to be in one of those V alphas, right? F bar of Si is the unique value that is contained in one of the V alphas. So let us denote this V alpha to be V sub alpha 0, okay? Which means that we are assuming that F bar of Si is contained in this unique slice denoted by V sub alpha 0. Okay, good. Let me erase this part. This guy is our equation number 3. Now, we define F bar of S for S belonging to this subinterval Si to Si plus 1 in the following way. We write F bar of S to be equal to P restricted to, P restricted to V sub alpha 0 to the minus 1 composed with F evaluated at S. It's equation number 4. It makes sense since, P restricted to V alpha 0, V alpha 0 is the unique slice that contains this F bar of Si, okay? So P restricted to this V sub alpha 0 is the homeomorphism from V sub alpha 0 to U sub x, okay, according to the definition of a covering map, right? Okay, so since it's a homeomorphism, we can call for the inverse, and this is precisely the inverse of the underlying homeomorphism. And that inverse composed with F is defined as F bar. Okay, let me check very quickly that this is a sensible definition. Indeed, if I compose P with F bar, and then evaluate this composed map at S, I see that P composed with P, P restricted to V sub alpha 0 to the minus 1 composed with F at S, P composed with the inverse of this restriction is going to be the identity map, right? And this is nothing but F evaluated at S. Right? This is exactly what we want for a lift to satisfy. Okay, so this we are good with the definition. Now this F bar defined in 4 is easily seen to be continuous, because this is a homeomorphism and this is a continuous map, and the composition of two continuous maps is a continuous map. So F bar is continuous. Okay, and so we have thus constructed a continuous map on each of these subintervals, right? For I belonging to this finite set 0 to all the way up to n minus 1. Okay, so we have this F bar defined on S0 to S1, then we define it on S1 to S2, and then we define it all the way up to Sn minus 1 to Sn. Okay, so F bar is defined on all these subintervals, and these are closed intervals in 0, 1, right? And F bar on the overlap of any two subintervals agree. Like if you take this pair, they are going to intersect at S1, and F bar on S1 is going to be the value of F bar at S1. Okay, so this way we see that by pasting lemma, F bar can be extended on the whole of 0, 1. Okay, so this is how we show the existence of a lift on 0, 1. Okay, and now we need to show that the construction, this inductive construction actually yields a unique lift. I mean that if I construct any other lift F tilde, then F tilde is going to be the same as F bar. That will prove that the lift that we construct inductively is indeed unique. Okay, so let us prove the uniqueness now. So let me erase everything. So the uniqueness of this lift that we have just constructed can be shown in inductively as well. Okay, so this is again an inductive proof, the proof of uniqueness of F bar. Okay, so let F bar is another lifting of F beginning at the same point E0 of E, so that F tilde of 0 is equal to E0 equal to F bar of 0. Now suppose that this is going to be our base case. Now suppose that F tilde of S is equal to F bar of S for all S belonging to this subinterval 0 to Si. This is the base case. All right. This is the base case of the underlying inductive construction. We want to show that F tilde of S is equal to F bar of S for all S in Si to Si plus 1. If we do that, then it will be proven that F tilde of S equal to F bar of S for all S belonging to this interval 0 to Si plus 1. Okay? So we just need to prove that this holds, right? Then we'll be done with the inductive construction. Inductive proofs that the lift is such a lift is unique. Okay. All right. So let's do it. So we need to prove that F tilde of S equal to F bar of S for all S in Si to Si plus 1. Okay, this is what we need to prove. Okay, so so let us recall the construction of F bar. So recall that we have shown that F bar of Si belongs to a unique slice, and we denoted that unique slice by V sub alpha 0, okay, for some alpha 0 in the index at J. This is what we have seen earlier. And we have seen that on this sub-interval, we have this definition of F bar. F bar of S is P restricted to V sub alpha 0 to the minus 1, which means the inverse of this homeomorphism composed with F at S, okay, which is nothing but P restricted to V alpha 0 inverse of F of S, okay. Now the question is, what can F tilde of S equal for S belonging to this subinterval? So this is the question. Okay, this follows from the construction of the lift F bar, okay, which we did earlier. Okay, so all right. So let me draw a diagram very quickly. So from E to B is the covering map B, and there is this map, a path in B, right? That starts at the point B0, right? F, and we are assuming that there are two lifts F bar and F tilde starting at the point E0, okay, and this is the commutative diagram, okay. So we have previously seen that F of this closed interval, meaning that the image of this closed interval under F is contained in U sub X for some X in B, right? For a given I in this finite set. We have seen it earlier, okay? With U sub X being evenly covered by B, this is evenly covered by P. Okay, so therefore, you see that, well, from the definition of lift, since F tilde is a lift of f, we must have P composed with F tilde to be equal to F. So we are just replacing F with P composed with F tilde. So we're writing P composed with F tilde at Si to Si plus 1 is contained in U sub x, okay, which means that F tilde of this closed interval is contained in the inverse image of U sub x under P that can be written down according to the definition of a covering map as a disjoint union of open sets in E. Okay, this is our equation number 5. Good. Now recall from points of topology. Let me give you the reference. You can look up page 150 by the same book by Munkres. Theorem 23.5, okay, which tells us that continuous image of connected space is also connected. Okay, so you see that this is connected for every I here, and F tilde is supposed to be continuous. So F tilde of this connected set, the image, F tilde of this guy is also connected, right? So which means that according to this result of points of topology, F tilde of Si to Si plus 1 is connected. Okay. Now you see that F tilde of Si to Si plus 1 is supposed to be contained in the union of all these V alphas. And V alphas here are pairwise disjoint. So this guy needs to be, since it's a connected space, right? It needs to be in one of the V alphas. It cannot be spread out over a bunch of V alphas since it's connected, and V alphas are pairwise disjoint. Okay, so this has to be contained in one of the V alphas. Okay, so let me erase this part, bottom part. So F tilde of this connected space has to be contained in V alpha for some alpha in J. Good? Okay. Now recall from the discussion following equation number 2 that when we were constructing this lift F bar, we chose F bar of Si to be in the slice V sub alpha 0. Okay, and from the inductive hypothesis in this case, and from the inductive hypothesis for the proof of uniqueness. Since F bar of Si is equal to F tilde of Si, right? So this follows from the inductive hypothesis. That's right. So let me recall the inductive hypothesis. We chose that F bar of S is equal to F tilde of S for all S in 0 to Si. This was the base case. And since Si is included in this closed interval, we must have F bar of Si to be equal to F tilde of Si, right? One must have F tilde of Si to be in this slice V sub alpha 0, okay? Alright. So now, since we want F tilde, the image of this closed subinterval under F tilde to be in one of the V alphas, and we know that F tilde of Si is already in this slice V sub alpha 0, which means that the image of this subinterval under F tilde should also be in this slice, okay? So we must have F tilde of Si to Si plus 1 to be contained in V sub alpha 0, the same slice. Good. Okay, we have gotten this far. So in other words, for a given S in this subinterval Si to Si plus 1, F tilde of S is some number Y0 that should be contained in V sub alpha 0, okay? As long as S is in this interval, we must have F tilde of S to be contained in V sub alpha 0. Okay, but since F tilde is a lift of F, one must have P sub V alpha 0 of F tilde of S to be equal to F of S, okay? Which means that P restricted to V sub alpha 0, it's a restriction, P restricted to V sub alpha 0 of Y0, okay? F tilde of S is Y0. Y0 is equal to F of S, so that one gets Y0 to be equal to P restricted to V sub alpha 0 to the minus 1 of F of S, okay? Okay, so it's important to see that here I'm not writing belonging to, it's generally a set, okay? it's a one element set, since this map is injective. In fact, it's bijective. In fact, it's bijective since it's a homeomorphism. Be restricted to V sub alpha 0 is a homeomorphism, so it's an equality. That is the reason it's an equality. Okay. All right. So so we have just seen that y sub 0 is equal to p restricted to V sub alpha 0 to the inverse of this p restricted to V sub alpha 0 of f of s, right? And this guy is nothing but f bar of s, according to the definition we had for f bar. Okay, it's using 4, but y0 is f tilde of s, right? Therefore, we just have seen that for all s in Si to Si plus 1, f tilde of s is equal to y0 is equal to f bar of s as required. QED. Okay, good. So we'll be having more results on liftings. So let us take a break here. We'll get back to you with some more results on lifting of paths and lifting of homotopes in the next segment. Thank you for attending the